Okay, so let me just begin by discussing a sort of model which will hopefully recap some of the things that we discussed last time. This is one of these models called the PSSY model, Pennington, Schenker, Stanford, and Yang.
I'm so sorry. Since you gave such a beautiful review last time, and I'm sure it will continue, are you thinking of writing this up? Because that's part of the tradition of the Infosys lecture.
Is that right?
Sent by David Tong, his famous lectures on the quantum Hall effect.
Oh, is that right?
Were given as part of the more or less similar series.
Okay.
Yeah, please do.
We should have fired it.
Yeah. Sorry.
I know the non-committal nature of that.
I'm hoping someone's taking notes. Then that's an easy.
All the students,
Okay. So this is a simple model. It's basically a two-dimensional model of gravity, just JT gravity, which is coupled to these end-of-the-world branes. So the way to prepare a state here is just do the standard thermopile double-like trick, but you end the state at some sort of insertion, which you can think of as this end-of-the-world brane, some operator insertion I, which in the bulk has a description as an end-of-the-world brane. So the standard rules would tell you if you want to compute, say, so this is the state we can define as I. If you want to compute something like the norm, then you would fill up this path integral as follows. In general, so let's say I wanted to compute the overlap psi j, psi I. There would be some label j and some label I. And this is just some Euclidean evolution of some length, say beta over 2. And then the rules of the path integral tell you to fill this in. So the standard natural thing to fill this in is with it's just the disk. There are higher topologies and so on that can contribute to this, but roughly speaking, this is what's important here. And this thing is only, so this insertion carries some label, and we're assuming that this is some orthonormal set of labels. So I and j, if they're different, then this overlap is 0. And if they're the same, then it's 1. So this thing will basically be something like delta I.
So can you
explain
a bit more the setup?
Yeah.
The picture is supposed to represent what?
So to cut this in half, this bottom half is supposed to represent the preparation of the state psi I. So this psi I is a state which you can think of as like in higher dimensions you would think of as a boundary state or something like that, where you have some insertion which is basically truncating space, some boundary condition here. And then there's some Euclidean evolution which goes up to here. So there's only a single boundary here, which is right out here on the right side. And so it's preparing a state in that CFT, or here it's just a quantum mechanical system. So it's preparing a state there. That state is labeled by the insertion I. And the bulk description of that state is that it's basically a black hole. So this thing, if I continue to Lorentzian, so this geometry will look like this. Basically be like a black hole with an end of the world brane sitting behind. And there's some horizon out here. There's something behind the horizon, and this thing carries the label I.
And sort of why is state? So what say a little bit more about what that I is there?
Yeah, it's not so clear. So here it was just a model where they were imagining that there's some kind of global symmetry or assuming some sort of flavor index that's living on the brane. It wasn't very dynamical as such. It didn't carry, they just fixed some definite mass for it. It was just like a world line action that you're integrating over. And the only thing that I carries is some sort of flavor label. There was no dynamical information in it.
But very roughly, can I think of it as a particular black hole state?
Yes, that's right. That's how they were imagining it.
So in n equals y angles, it's a particular state.
Yes, exactly. So we can think about this in higher dimension. We can imagine just some specific boundary condition in n equals 4.
So a particular state.
Okay.
And why does a particular state, why is it represented by an end of the world brane?
So that was just a model here. So here it was just they were modeling these things as end of the world branes. It depends on what that particular state is. Like in n equals 4, if you had something like a Cardi boundary condition or something like that, it could be represented effectively in gravity as some sort of end of the world brane with some tension and other action on top of it. So that's just a model for what the bulk looks like.
But is it what I want to understand is it sort of a reasonable model? Is it?
Yeah.
One thing is, how do you know you can consistently quantize JT gravity with any end of the world.
Oh, that's because they did it. Like there's a version of Sachenko Stanford which they did.
Isn't a consistent quantum path integral defined? What are the properties of the end of the world?
That it just carries a mass. No, it has a very specific mass. You just fix that as a parameter.
There's a consistent quantization of JT. What are the precise boundary conditions? I mean, define the path integral.
The path integral is defined. So the action is completely defined. The gravitational action is the JT gravity action plus the action of the world length with fixed
What are
mass.
boundary conditions for the dilaton and the metric precisely on the end of the world plane?
On the end of the
Yeah.
world, yeah, it's the basic. It's essentially that it's on geodesic, so it's k equals 0, and the jump in the dilaton is given by the tension.
And there wasn't a precise definition of the measure or precise.
Okay, the measure is another thing, but
define the quantum. Is it the case that a quantum theory can just be extended to allow for any boundary conditions so easily? I mean,
So just before that, is there?
I'm giving you a bit of a hard time.
No, that's
because
fine. That's fine.
if the-
But we can,
No, but just in the boundary
Yes.
situation.
Yes.
In boundary can be, is there an independent description of the boundary theory and its Hilbert space of?
Yeah. So one example of
Because I
this.
remember that there was some characterization of the state with this gamma.
Yeah, there is an independent dependence.
And then they also show from the boundary that you can actually write down this locus.
Yeah,
Of
you can
this
do that.
end of,
So-
you can actually see the world ending there, right? I mean, that kind of goes towards what Sandeep is saying.
Yeah. So
But for that, I want to know first in the boundary what it is and what is
So the way these states were actually originally proposed was from this paper by Korkulu and Maldacena, which worked with SYK. So instead of doing JD gravity, let's work with SYK. In SYK, there's a very clear understanding of what these I's are. So what you do is basically consider these bit streams. So the SYK is labeled by some fermions. You can label them by zeros and ones. And then you just project onto some set of zeros and ones. You pick some bit string and project onto that. That is some boundary condition that you're imposing there. And they argued that the bulk dual of that is some sort of brane that's starting from this point.
And
With some tension, some
what
fixed
is the
tension.
nature of that argument?
Yeah.
Just very roughly.
Let me put it like this. The low energy limit of SYK, which is a well-defined
Yes.
object,
Yes.
is equivalent to JT gravity with no end of the world. Okay, this is an exact statement. Absolutely. The partition function computed at low temperatures in JT gravity
Yes.
is reproduced
That's
as a gravitational path integral of JT gravity with no end of the world break.
That's right. If you did
Quantum
just
mechanically, exact to all orders
Yeah.
and
Pick
non-perturbatively.
the state, right? You have to
yeah,
pick the
if you
state.
just did the partition function, that's fine. But
But
here,
I mean,
this is
you know,
some.
all degrees of freedom must show up in the partition function at finite temperature, and there are no end of the world branes in the path integral which agrees with the SYK model at low temperatures
Yes.
to non-perturbative as an
Yes,
exact
but
statement. So
this-
what is this object?
this
It
object-
changes the partition
In
function.
SYK, it's a very high energy thing, right? In SYK, if you're projecting on some definite bit string, that's a very high energy
No,
state.
okay, but
So it's
in
not
JT
necessarily.
gravity,
That's a separate question. Let's talk about SYK first.
Okay.
Let's talk about SYK first.
Okay.
There we agree that there's a well-defined prescription on the boundary for what the state is. Then we can ask about the bulk.
So it is clear, yes.
But wait, what's the problem with the boundary thing?
No, it won't affect the low energy limit if it's going to agree with JT. Okay, all I'm saying is this. You can either augment SYK,
Okay.
okay, with extra degrees of freedom.
No, I'm not augmenting SYK. We're just projecting onto bit strings of fermions that existed in SYK.
Then how can it be, given that the SYK model at low energies is exactly equivalent to JT with no extra degrees of freedom? Okay.
Well, because we're not in the naive way of taking a low energy limit. We're adding some extra high energy excitation and then taking the low energy limit.
What does that mean? The high energy excitation won't be there.
Why? I don't understand.
Either it's, if I added a Planck scale excitation, it's
Yeah.
irrelevant for computing the partition function in the room today at temperatures of, the 200 degrees Kelvin.
I guess it depends on what calculation you're doing. Like you could
The
compute.
partition function. I mean, SYK is not equivalent to JT gravity by any means. Only the low temperature limit in a very precise sense is equivalent non-perturbatively to JT gravity. Okay, this
Yes,
is
yes.
No end of the world brane enters in the JT path integral in that equation.
That's right.
Okay, so now how can you claim that, now I could understand a statement which says SYK change with extra degrees of freedom at low temperatures becomes equivalent to a new theory of gravity with end of the world branes. Okay, that's a possibility, but then please define
That's not what's being said.
That's not what's
Yeah.
So then what's being said? Okay, we should go on, but I
don't understand why I'm not allowed to add some extra. It's similar to just saying,
No, you are allowed to, but either define it on the gravitational side exactly, which maybe they've
on the
done.
gravitational side, it's being defined by setting boundary conditions on the brane with some specific tension that's being specified. On the gravity side, forget about the boundary rule for
And
now.
what are these degrees of freedom I and J on the gravity side? How do you define a path integral with these degrees of freedom?
It's just going along for a ride. It's just like some degree of freedom that's been carried by this.
Exactly is the action. Root G phi R minus lambda plus what?
Plus
M
integral of
d tau.
the
with some
action
I.
of the world line is just some mass times its like
Yeah, and where does the I degree of freedom come in this?
this is true for all I.
So I can take arbitrary values.
Yes.
And the theory makes sense.
I mean,
what is it?
you can
what is the
consistently
statement?
find all partition functions and overlaps using these rules. There's a
It's like JT coupled with some massive particle or something.
Well, then there's an exact action del phi square plus whatever into D for the massive field. Okay. And n
Sorry,
flavors.
what
n-
massive? What massive field?
I mean, I'm saying I understand the action where you have a massive field, say psi. or-
Yeah, but this is not a field. This is strictly in the limit where you're localizing to a word line. So it has a word line action. In that limit, it's JT plus that object. That can be consistently quantized. And there is some non-perturbative quantization of that. You can question whether this is a reasonable model for higher dimensions or the sort of thing Shiraz was asking, but that's not what you're asking.
I'm just saying, I mean, for any number of degrees of freedom, this constitutes a consistent theory of quantum gravity into D.
Yeah. I mean, depends on what your definition of consistent is. It'll give you something very much like JT gravity. If you're happy with JT gravity as a definition, then it's the same as
You
that.
have a different partition function at finite.
No, I'm saying it's as consistent as JT gravity is.
I don't think so. Okay, what's the
Can I-
partition function anyway as a function of n, beta? How does it change?
So can I define this theory to be a JT gravity, I mean, at least at the level of being able to compute partition function? Can I define it to be JT gravity plus coupled to a bunch of massive, very massive scalars, so that you just approximate them by geodesics, and then you compute the path integral by summing over all their world lines.
Yeah.
In
You can say
addition
that.
to JT geometry.
That is a definition, but that's not exactly what's done here.
I mean, here what's being done is the approximation to that sort of thing. With like, it's just technically much easier to deal with. I guess in principle you'd want to do something like that. It's very hard to quantize that thing.
Why is it coming out of the boundary then?
Sorry?
So loops of your well lines being the bulk.
Yeah, there would be the
No, but I mean, given that the bulk theory is defined this way, now you can ask what is this, how would I create that particular state on the in the bulk, right? Assuming that there is some AdS here too.
Yeah, it's some source
Then
for that
some
field that's
local insertion there. That we-
Yeah.
It's a source for that field at the boundary.
Yeah, at the boundary.
And the boundary sort of, okay, so
I mean, that's one-dimensional boundary, right? So there's no other way to
So,
insert
I
it. But
mean, you would just add that
but we
action
ended there.
and, it could choose in that limit some geodesics. You'd have to
Yes.
sum over all geodesics
yes.
and try to define it like this.
That's right. This does that. This sums over all those geodesics weighted by this action, etc.
there's a very large number of such paths. That's your
Yeah. Yeah, that's not, I was thinking.
Yeah. There's different choices of these. So there has to be some flavor index on that field that you're talking about, which will carry that.
Go on, but it's if you try to do it exactly with a massive particle, it's very hard to make sense of
But
it.
if you did what Abhijit saying, you'll also have loops at the back.
That's right. So
And
what
you
is
have
being
loops in the
neglected?
bulk. Yeah.
What is being neglected is loops in the bulk, and so it's under the approximation that it's actually a free field in the bulk. But in principle, you should include it.
It's heavy, that would cost. If it is heavy, that would cost, right? These loops would cost a lot.
These loops will
So because of the field itself,
The field.
I guess it depends on the coupling.
No, but you'll couple it gravitationally if it's a free
Yeah.
field. You couple it gravitationally.
No, but the field itself is free.
Field itself, I was thinking, yeah, that would be the simplest thing.
The field itself is free, right?
Yeah, I was
Yeah,
thinking, I mean, I don't know.
Yeah, then it's fine.
Yeah.
What I'm neglecting here is interactions of the field with itself, like loops of the field
So
itself.
these loops just by itself circles, I mean.
That is not obviously suppressed, I guess, because it depends on the interactions that you write down.
No, I mean, it will couple to gravity in a certain way, right? So you would, for example, if it were to have a loop, you would draw a circle there and drill out a hole, and then you have a new geometry with that circle as the boundary, and that would be suppressed, right? See, even as a
I mean, it could be, but it depends on what the loop diagram is like, right? Like that diagram could be large.
No, just a circle. There is no 3-point vertex. Just a circle. They are not interacting with itself.
Oh, you mean just like here?
Yeah.
Oh,
Bunch of holes.
I was saying I'm neglecting this as well. If
Yeah.
that exists, then this problem.
Here's how any reasonable field theorist could solve a problem of gravity with a small cosmological constant
Yeah.
and Planck scale particles. You would integrate the Planck scale particles out.
Yeah.
You would construct a gravitational action with all possible terms, with the higher irrelevant operators suppressed by the mass of the particle. Okay?
Yeah.
That would be Wilsonian exact way of doing it, and you'd compute it.
What if I need a high energy state? What if I'm interested in studying the high energy state?
As long as all black holes and configurations you're interested in are big, if you're talking about high curvatures, then they will come into play. Okay. Anyway.
I don't think this is particles are usually these gauge invariant, ON invariant objects, right? This was meant to be one of the microstates. I feel it's different.
Yeah, it's different.
It is meant to be one of the microstates, and the microstate is because it's carrying this extra label, right? So there is this I label which wouldn't be ON invariant, as you said.
Yeah.
And it's carrying that label. But the bulk description of it is still approximately this thing. Like
Microstate would be a word, right? I mean, but if you want to write down the theory, then this theory, that action plus this action, that looks like an action particle.
You should go on, but I'm just saying, if the idea is, look, there are microstates, they're hard to describe, and we are creating a cartoon for it. I don't know. Okay, and the lessons are general and so.
that's all I'm going.
But I mean, if the claim is that it's an exact theory and we should take it very then the bar has to be a little higher.
I don't think anything here is going to depend on it being an exact theory. It's a separate issue, which I don't think is going to be.
Apparently solves the information puzzle that
it's just clear microstates.
That information is retrieved, and if you have a quantum mechanically inexact theory, which is at the bedrock of our proof that information comes out, then I'm sorry. It's not a good starting point.
Well, then we're doomed because we don't necessarily have a consistent quantum gravity theory to even ask about.
There are many quantum mechanically consistent 2D gravitational theories. You want them in asymptotically flat space, we'll give it to you.
Yeah.
Prove it there.
Yeah, I mean, the features that we're going to talk about.
Sorry?
If it was something that's already.
But they're well defined. No, the claim is a tall claim, right? Okay, please go.
It depends on what level of precision we want to work with here. Whatever I'm going to say is going to work for those models as well. The features are pretty general.
Please show me in CGHS,
Yeah.
which is a precisely
Yeah.
defined quantum theory of 2D gravity.
Yeah.
Asymptotically flat, that information comes out and there's no loss of info.
I mean, there's going to be islands there as well. What's the? You can calculate it. I don't understand what's the issue.
It's far from clear. You will need some way to model the microstates.
Sure, we can do that. So we can create many different microstates.
It's just, I can give you the action. You don't
Yeah.
see the microstates. You'll see the mechanism entropy without the microstates.
No, but you can have many different matter configurations in the bulk, which can potentially beat the Bekenstein-Hawking entropy, for example. Whenever that happens, there'll be an island which will come in because, I mean, it's just it's the same mechanism. It's the same wormhole that's going to give you that action. I'm not sure what
I don't think so.
specific issue is.
I don't think you can just say that this argument applies in general and so on. When you use the specifics in this.
No, we're not using the specifics. I started by saying this is a toy model.
You're modeling, I mean, I think what Shreya said is also my understanding.
There's a concrete calculation of
actually having a theory which, in fact, shows you what the
The appendix there, where they take this SYK state.
Yeah.
I remember them doing some geometric analysis to show that actually is the word line of that state.
Yeah, so what
Right? There was something there which comforted me a little bit.
They propose that psi I is basically given by the following. It's just a sum over states with some random coefficients.
But didn't they augment the XYK degrees of freedom?
No, these are just the original states. So if EJ are the states of the SYK or quantum mechanical system, it's just part of that. So the augmentation that you're talking about is just in these coefficients. So we're choosing some random coefficient Cij,
That's right.
which is labeled by some I. So I can choose different sets of random coefficients
But the fact that it was this gamma function and all that.
Yeah,
it
so
ended up being
just take
important,
this,
right?
just take this and compute all the norms you want, like all the overlaps, etc. What they showed was it matches exactly with GT gravity coupled
No,
to
but you
momentum.
actually kind of see that you can kind of compute that length or something, right? Where the world is ending.
Yeah. So there's some action. It has to be in the limit where this mass is large. The limit is in the limit where the mass is large. You can basically completely quantize this. I think maybe even that's not important. I think even exactly in the mass, you can quantize this thing, and you find that it matches exactly the thing you would get by adding in this action.
No, I was just trying. I see. You get that with that.
Yeah.
Okay.
It's just like Sachin Stanford, where they show JT gravity equals this random ensemble. Here, you just add this extra set of states and try to compute their overlaps, plus whatever partition functions you like, and you again see that it's fluid to this particular
I
test.
see. So one can, instead of the SYK model, one can start with this.
Yeah, you can start with the random Hamiltonian
picture, and then
Yeah.
from that
you
draw
construct
the
these states.
And the claim is that is being represented by such a overlap.
Yes.
Is that okay?
Well, you must go on. Please go on. Please excuse me, but I'll say this. SYK is not equivalent to JT gravity. Nobody knows whether SYK model.
But we're not talking about SYK.
Yeah, but let me complete. Nobody knows if SYK model is even equivalent in any exact sense to it in the theory of gravity. What is known and is precise is that the low energy limit of SYK is equivalent to JT gravity. Okay, if you take high energy states in SYK, they do not lie in the sector described by JT gravity.
Right now, we're only describing the quantum mechanical system that's dual to JT gravity, not SYK. We're only talking about the matrix model.
But
EJ are just the eigenstates of that matrix model. Forget SYK.
model. That is
So we're not talking about
exactly
SYK.
equal to JT, right? Okay. And then you can ask what is the state in that?
Okay.
And the claim is that that's this line, the blue line. And I don't know how that comes about, but that's
So the tension is related to what of the state? The tension of your line is
these
related
random variables, CJ has extra data in it, right?
Yeah, there's some functions that show up here. It's not just this, there's some gamma function, etc. that shows up here.
Right.
Yeah.
roughly energy, right?
Well, the
It can
energy,
take any value, the tension can take any value.
the energy is fixed here.
but depending on what CIJ is, right? Or the
Yeah. That's right.
And you can dial the tension as you like. I'm asking.
Yeah.
So there's an infinite set of such states.
Yeah.
For even for any given I, there's an infinite number.
By changing mu.
Yeah, by changing your tension. I'm asking.
Yeah, I think so.
So his point will be that it's an overcomplete.
It's by far overcomplete. Already with I, it's overcomplete, and then with that, it'll be even more overcomplete. But yes, the claim is that would be the overlaps you compute in that would be given by this bulk theory with these n properties.
And so this is saying that, roughly speaking, the average microstate will.
Yeah, that's right. That's right.
Microstate with a given energy.
That's right.
So what's the bottom line is that there is a precise understanding of each microstate on the gravitational side as end of the world brings.
No, I think this is an effective model.
Each. I think what he's saying is that if you take microstates and average in some energy window around some particular end.
That is one way you could do it. Here, the averaging ends up being averaging over the set of energies themselves because you're averaging over this random matrix.
Yeah.
That's another averaging which you could do, and that will have this effective description.
But there's the matrix and there's the CIJ.
Yeah.
And the C is also averaged.
Both are averaged.
Yeah. So this is the one I'm talking about. I'm talking about the C's. So there is some averaging over some window of energies.
Yeah.
And if you do some averaging appropriately, apparently that has some.
But is the idea that you augment the SSS matrix model with extra random variables? Or what is the idea?
No, you take.
Yeah, you could call that. I mean, the CIJs are extra random variables in the sense you're picking a state in that model, but it's a random state. So there's extra randomness because of that.
Already the random theory.
It's already a random theory, and in the random theory, you're picking a random state.
Yeah. And the claim is that there it's very clear geometrical descriptions. Why don't we?
Already this random, so one has to kind of work in that setup, right? Where the dual is not a field theory. So we cannot really talk about precise microstates, but rather some ensemble, and then there's some state in that ensemble.
It's good.
Yeah, so kind of
can get to.
Yeah, but at some very rough level, you take one of these Hamiltonians, you take some typical state.
Yeah.
And this is more or less.
This is expected to be like if you. So in this Korkul-Maldacena case, for example, what they did was basically take some typical SYK Hamiltonian, pick this bit string, typically try to compute correlation function, we find that it's consistent with this picture to some approximation.
And so, because this works, you say that the expectation is that something like this will work in n equals form. You take average.
Yeah, I mean, so the expectation here is that this is the key point that's going to end up here is that there is some sort of high energy insertion here, which is leading to this behavior where it's some non-trivial state behind the horizon. That's what's going to be important.
Then why not just say you have what in gravitation would appear like a smooth geometry with a smooth.
I'd say that I was just giving a toy model.
No, I understand, but why there's no end of the world brain on the gravitational side. It's just your accounting. Strominger-Waffa in the SSS theory.
There are end of the world brains. There are end of the world brains in higher dimensions. Like I don't like in n equals 4, you can have these geometries where the sphere caps off.
Conceptually, the statement is GT gravity equals SSS, and you have a black hole with a Hawking-Bekenstein number of states. The counting of that state, those states in the underlying microscopic theory is this. It's like, string theory accounts for D1, D5 black holes, which are nice smooth geometries, and the microstates are the strings. And they're excited, isn't it? We don't say even the type 2B string theory will enter the world brains.
What's one particular state of that?
Yeah.
Yeah, I mean,
there are end of the world brain states in high dimension.
I'm just saying, we don't say that because there's a Bekenstein-Hawking worth of states for a Schwarzschild black hole, there are end of the world brains there. No, it's, in some picture we have a nice Lorentzian geometry with a smooth interior. And the outside it looks miraculously like you have Bekenstein-Hawking worth of states.
That's right.
Which you can account for in the hologram. That's what you're saying.
All microstates need not look like end of the world brain states. Some of them will. And we're just looking at them. I don't see why it's particularly important that it's an end of the world brain state.
Just say this is how you're counting the states of SSS. This is another basis to count.
It's not it's an over-complete set of states.
It's an over-complete basis.
It's not so important that it was end of the world brains in the sense we could have had an over-complete basis of smooth states like you want.
Yeah. Which are mysterious on the gravitational side.
That's what exactly saying. That is mysterious. How to count them?
Very hard to count. And nobody knows how to count Strominger-Waffa worth of states on the 2B side. We count them in the D1, D5 description.
Well, I mean, in any black hole at late times, you have a huge interior and there's a huge number of modes. Just count the number of photons that you have there. That's already huge. And just consider all possible states of that.
And that's already right to do, but you can't be putting end of the world brains to do it.
That's a separate issue. But I thought the issue was having even an explicit version of smooth states which have this number.
But this is a more accessible one because you just take this state in the SSS model and just see what its gravitational dual is.
There isn't a nice gravitation.
Well, he's claiming that it corresponds to like particles of this type.
That's a claim. There's no basis for that claim.
There was some calculation in that. There was some calculation in the
There is
appendix.
a precise claim
Where
this state
shows
behaves
that-
like particles.
Yeah,
Sorry.
that if you start going this way, you start the descending end here. I remember something like that in that thing.
Thank you, please cover it.
It's a waste of time for you all. It's a waste of time.
You don't miss anything. I missed you though.
Sorry, please. I apologize, Pratik. I really apologize. Sorry. Please go ahead. Okay. These states I understand in it.
Let's think of
No,
this.
sorry, maybe we can have that's
Yeah.
So
Okay, I was
We're debating whether PSSY is a reasonable model.
No. I was giving him the hard time that I've given you and you answered me and he answered me. Which is to say, in what sense these are the states in the SSS matrix model, which are supposed to account for, say, black hole entropy and so on. Why do they correspond to end of the world brains? I mean, why not just say that they are just states of the black hole interior? Smooth, you have some smooth black hole geometry. Okay. And you're trying to account for S. Bekenstein-Hawking, and these are the states in the hologram.
Yeah,
Where does the statement, that there's actually the end of space-time there come from?
right. That comes from the fact that if you calculate the overlap, I think maybe you've said this, but let me say it again. You calculate Ix-Ij overlap, and then you average over the Cij, then you average over the so on. Then you can show that the resulting amplitude basically corresponds to having some wave function on that view. And that wave function looks like that of a tension, some object with some specific tension, which is given by the parameter mu, which is floating somewhere here in the general average. So you can pretty explicitly show that at the gravity level, it looks like some Hartle-Hawking type wave function with some tensionful objects.
So you take, you have a way of preparing the psi state gravitationally. Huh?
Psi is this.
Well, psi is this, I have no issue in the SSS metric model.
Correct. So now you do all the averaging and so on.
Yes.
So once you do all the averaging, now you're left with the gravitational average.
Okay.
And that's
for the inner product.
The inner product, partition function, whatever.
Average.
Some average of.
Okay, now you have to translate on the gravitation.
Yeah. So on the gravity side, you can interpret that as having some boundary condition on that.
For the dilaton and the metric.
Correct.
Because those are the only degrees of freedom.
Correct.
Okay, what's the boundary condition that corresponds to I? Oh, you have averaged over I.
I and so I and J are some indices. So those are there. Those are like some flavor indices. But in addition to that, there is some particular boundary condition in the boundary that will, as you say, and the dilaton and the metric. And that, yeah.
And what is I and J on the gravitational side?
It's just some.
It's just a flavor lift.
So you have augmented JT with the flavor.
Yes.
So with the end of the world brains with flavor indices. Yes.
But not augmented in the sense that extra, right? I mean, it is there in the SSS model.
But no, with the pi theory, I mean, if you computed only like partition functions, there's
No, I mean, because that the SSS model is completely equivalent.
Yeah, absolutely.
To JT.
It's secretly there somewhere.
Already there.
It's secretly there somewhere.
Already there. You have
That's
not augmented somehow.
That's
It's
right.
just that you have never focused
You
on.
never computed things which cared about that.
Right. And then, yeah, so I just maybe to complete on the gravity side, there is a particular boundary condition that you have to put on that blue line. That there's a natural boundary condition that corresponds to tensionful object that you can decide to call an end of the world plane if you like. You can just think of it as some boundary.
And in Lorentzian space, you would never reach it causally from your boundary.
No, you can reach it. You can
Reach
it. In this case, it's behind the horizon.
It's behind the horizon, but you can reach it. You can't get out then.
No, but can you reach it? Your diagram looked like it was even.
Maybe that's not important. That depends on the tension, like where it is exactly depends on the tension.
So it sort of cuts off half of the Penrose diagram. Is that right? That instead of going up, let it be an eternal black hole.
Right. Some fraction.
You can actually even make it sit
You can make
Well behind the
Yeah,
horizon,
right there.
but it cuts off.
That's
other part.
yeah, it can be right behind the
So this is a physical lesson that an average microstate does not have the other side of the.
That's right. It can't, right?
Yeah, it has to be a pure state black hole of some type. So it can't have another boundary for sure.
Right.
Now, what else is behind? I mean, it could be an end of the world brain, something that caps off, but that certainly doesn't have another asymptotic boundary.
But you're giving a prediction for roughly where space time is.
That's right.
In this model, yeah.
That depends on the choice of
It will
algorithm.
depend on the details.
But I mean, the claim, at least in JT, is that what you would have thought of as if you just constructed the gravitational solutions, solving Einstein's equations for a black hole, you would say there's a smooth interior. And okay, if I declare that some value of the dilaton corresponds to a singularity, there's a singularity. Everything looks smooth.
No, it doesn't have to. I mean, in higher dimensions, we could have prepared a state which was like this with a heavy operator insertion here and so on. So I don't see why it's
I
like.
start with phi r minus lambda. I solve the gravitational equations. I get a smooth black hole.
Yeah, if you did that,
Which
then
has
that's.
S. Bekenstein-Hawking as the area analog,
Yes.
right? As the entropy. Okay, everything's smooth. Now you're saying that actually there are other solutions.
Yeah.
Not to phi r minus lambda, right?
No,
Because I know all
It's
this.
that, but with augmented boundary conditions.
So now I change the theory. I would say this at least. I change the theory. I add extra degrees of freedom with end of the world brains, and that is equivalent. Now I look at solutions in this theory, and they are equivalent to the original theory and account for aspects. I mean, this seems to be the list. Okay, anyway, please go on.
For one side.
For one side, right? Yeah, I only care for one side. So
Already can postpone the
Calculation is for a two-sided. This calculation is for a two-sided.
Yeah, in JT gravity, there are no one-sided.
Because I solve the Lorentzian theory, I construct back inside.
In Lorentzian JT gravity, there's no one-sided black holes.
You mean without end of
Without end of the world. There just isn't such a solution.
You have the dilaton get to be, some value in the future.
take the disk.
I mean, I always have two boundaries, right? Like it'll always be like a thermophile double like state.
If you're thinking of the disk, then analytic determination of the disk, the two boundaries.
Yeah.
Yeah, that's two boundaries.
When you have to somehow cut off that other boundary in order to get a one-sided one.
So this is very specific to that.
It's very specific to 2-dimension. Yeah, that's why I didn't want to focus on that one.
So the claim is that in JT gravity, if you took one-sided solutions, then you think it makes sense by augmenting. And if you take the two-sided solution where you'd have a smooth geometry, you would get an Einstein-Hawking entropy at each end in that theory. But then to account for it, you would have to augment the theory itself somehow. Okay, anyway, go ahead.
Saying, I think it's still already part of the non-perturbative theory. So you maybe didn't see it in the disk quantization as such, but okay, I will go. Okay, let's move on. So here so just to get everyone thing back again. So the overlap psi Sij is computed by this disk partition function. So we had some boundary conditions I and j, and then we're filling it in by whatever geometry fills that in. We assume here that I and j are orthonormal, so that psi Sij is just given by delta ij. So if these don't match, then there's no overlap. Now, with the same rules, you can try to compute something like mod psi Sij squared.
One quick question.
Yes.
Suppose one were to make your states with like a delta function in energy. It was very narrow.
Delta function.
Then you know what would happen. Focused on a particular band of microstates of a particular
Order one or exponentially?
whatever you know.
Because order one, it's fine. If it's exponentially small, then I think it's going to end up being one of those things where I think you can compute the average thing, but it's not self-averaging. Like it's not characteristic of a typical instance because it'll depend on the details of whether there was an energy state there or not.
But as I make this window smaller and smaller,
Yeah.
does that do something to your diagram?
No, I think this diagram itself will stay the same. I mean, there are some higher genus corrections to this.
No, I'm saying
You
roughly.
may ignore that.
Yeah.
So this thing will stay the same. But like you can try to compute like the variance and so on, and it may change.
Sure, that's all right.
But yeah, this shouldn't change too much, I think.
Interesting.
I mean, when it's exponentially small, then I am not sure. But
You're trying to get it really one state, then you're saying. Like
yeah.
It's too much.
Then it's
But why do we ignore the other side? I mean, usually, when I have some boundary, I insert some operator.
Yeah.
I just insert it, right? I don't end the world behind it. On the boundary. On the boundary.
right.
But here, of course, it's one-dimensional.
Yeah.
You might as well end it or not.
Correct.
So I have a circle, I put it there. Then I could have imagined some picture of this sort also, right? There is this, and then there is this. And the same thing here.
So it's two boundaries.
Yeah, I inserted this operator. I guess it doesn't matter.
You
right?
could have done that. Yeah, I mean, if you just doubled this space, then you would have found things consistent with that. One picture for this is this Coulomb-Madison type thing, where on the left, let's say you have a left-right system. On the right, you want something like this psi state. On the left, you just project onto this split string. Now that is a violently high energy thing. So on the left side, you don't have any nice holographic description anymore. So you sort of forget about that and you just have this right side. It's anyway a product state with that. So it's never a connected geometry anyway. So you just look at that part.
Is what you're saying like psi I, psi j, mod square?
No, I think he'll change the definition of psi I to something which has another EJ here and maybe a beta or beta or something like that.
Just get the two
There's two boundaries there.
No, but if he wanted to do the calculation he wanted, there's just one E, then you get this, right?
This, as Pratik said, this is a two boundaries. That's a one boundary.
Sure.
And just as a boundary person, I insert an operator, right?
No.
So here I have a circle as my boundary, and I just insert an operator. And then it so happens that it becomes this in the geometry.
So that's another calculation. That's not what he's doing.
Yeah, no.
Yeah, that's not.
But it should be just take whatever you want and just adjoin this.
Yeah, I think
You
it's
can
roughly
make it
like
double.
just reflect
Yeah,
this
like that.
and then it's the same. Sure.
Because that k equal to 0. That's why it allows for moving.
Yeah, that's right. But there is still a jump in kiloton value, but I think that's fine. It's still finite actually. Okay, good. So we can try to compute this.
Sorry, you must want just to internalize what you all told me. Are you saying that Look, I mean, in type 2B or whatever string theory, if you ask me, account for the black hole microstates, I would say, oh my God, that's like some impossible, it's like you can't do it with Einstein gravity or whatever. But in GT gravity, one-sided, if you are willing to put in these objects, then
But I still you cannot account for the microstates, right? Because this is highly overcomplete. You can't use that to.
That's right. That's right.
You can't, but you use some way of
What you can do, I think, if I'm understanding right, is that if you take some suitably average state, you can see what the difference in the geometry between having that state and having having turbulence. And that difference is only way behind the horizon. So
Right.
for many practical purposes, you don't care.
Right.
But the prediction is that for a guy who fell into the horizon,
It makes a difference. Yeah.
That's
So
very
this is not specific to GT gravity. In Einstein gravity or whatever higher dimensional gravity you like, it's relatively easy to create an overcomplete set of states which just differ behind the horizon. This has been done like in many papers at this point. Yeah, you just add some heavy operators, whatever. Like, but it's not particular to GT gravity. So I don't want to upset on that point.
I mean, the claim is that you are accounting for all the states in some overcomplete way.
That's right.
Right?
In any theory of gravity.
And that's a huge claim, right?
Yeah.
accounting in some very average way. Right? What you're accounting for is where space-time ends. Where your space-time
For each of these particular or some average.
for these very roughly by their energy, right?
Yeah.
Yeah. So not very much. It's very cost-grained description.
It still goes through. Some descriptions.
Yeah, I should also saying if you try to go after a basis of microstates, one energy eigenstate, then this picture is lost.
Yeah. Don't expect a nice gravity picture. Okay.
So I want to make such states in 3 dimensions.
Yeah.
Then I would have to take 2-dimensional CFT and insert some line operator, maybe line operator.
Yeah. Exactly.
To break it down.
Exactly. Okay. So now we can go on. How do we?
This kind of thinking is at the root of Vijay Balasubramanian.
Yes, that's right.
All the
That's
different papers that
That's
you can account for
That's right.
Frankenstein by just creating
Adding these
things. You
shells
have
and
a
so on.
overcomplete basis, but you compute overlaps and you
That's
find what is the rank.
Once you have an overcomplete basis, you have enough to do everything there will go through. So it's not magical after you have that.
Yeah, and you all think that's reasonable. That instead of counting Bekenstein, Hawking, either in the hologram or in string theory, in closed string theory, in some impossible way, I'm just some guy. I live at low energies. I take shells of matter, and I do this, and I've really understood Bekenstein.
But how will you actually count? You have to do this island hand.
You have to do this thing where you compute like the resolvent, extract it from that. It's not like a literal state by state count. That's overcomplete.
But as you said, you have the overcomplete, and you do Gram.
You can build an overcomplete basis.
And you do this Gram-Schmidt by doing some island stuff, some crazy gravitational property.
Yeah, some gravitational quality.
Yeah, it's a normal thing, but
That's not well understood. What sense? That's a trick that you can use the rules of the gravitational path.
It computes the right number. It need not give you the exact
So
state.
in the same sense that Lukovitz Magazine calculated root again. It's a you use it, it gives you the right answer, but you don't.
Or Gibbons Hawking for that.
Or Gibbons.
Okay, I'll wait. I thought it was.
But as a gravitational person, we see very coarse grained thing, right? You just see, as Shiraz said, where the space is. That's it.
And some geometry, there's some geometry behind the space, like whatever's happening here, etc. Yeah.
So,
Like you could have had some profile of matter that you added, not just this plane. All those details would presumably be still there.
Sandeep was suggesting that it somehow feels like more because you can do this resolvent or whatever calculation to calculate the black hole entropy from here. But it's not that surprising because it's using the rules of the gravitational path.
Yeah.
We know that the rules of the gravitational path
Gives you
are smart enough.
those sort
Yeah.
of numbers.
Yeah, not necessarily counting.
Yeah, exactly.
Yeah,
It gives you the number
Without
without
insertions of these states on the boundary, you will get that kind of answer.
as long as there exist some states.
Yeah, exactly.
You don't have to say what they are.
You cannot
Right.
quantize a Hilbert phase space in gravity and get this number. Let's say that's right. That's not happening.
You just need the phase transition to the eye.
Yeah.
And then it's words up.
Yeah.
Okay, but anyway, you was going, but the claim was that resolvent computation done using the gravitational path integral doesn't need the entire UV data about the gravitational theory.
Yeah, just like Lukovitz Magazine doesn't need the entire UV data.
So somehow you can account for Bekenstein-Hawking just by doing low energy stuff.
That's-
Or Gibbons Hawking.
No, but it's not
Gibbons
that
Hawking.
Bekenstein-Hawking.
Gibbons
It's not just saying area. No, it's more than, I mean, Bekenstein-Hawking just said, okay, area must be the entropy because thermodynamics.
But that's
I think the extra thing is here that we're really computing an overcomplete set of states.
Yeah.
That's the new thing.
and computing the result and computing the inner product.
No, the fact that the number ends up matching is like old, right? Because it's Gibbons Hawking. The fact that you could construct such an overcomplete set of states is the new thing.
But do you think what I thought Hawking radiation, ingoing Hawking radiation?
It's not very new. It's like, okay, whatever. Like, yeah. It's not very new.
We are not counting that, right? We are not counting that to get a number.
I suppose something
We can count it in this manner where you account for the fact that they have small inner products with each other, so do Gram-Schmidt, etc. and count the right number. You can count that. Yeah, you can count that. Yeah.
Sandeep was asking, can you construct the orthogonal states in the bulk?
Yeah, I thought you know.
Or
Then how
I mean,
can
at least
you
it's
can
hard
compute
to
the rank without computing the state.
Yeah,
if you have an overcomplete set.
No, but if you have a less rank
But I'm
matrix,
just
you
saying you
can
diagonalize
diagonalize
it.
it.
You diagonalize.
Likewise, so it'll have some very complicated description.
But I thought in principle you do that. That's the way the talk was given, that you compute the overlaps, you can then figure out the rank as well as the orthogonal eigenvectors.
So in principle you could, but in the bulk it's really hard to see how that would work, right? Because everything that we're computing is an average. So what specific coefficients do I put in? Like it'll depend on the specific member of the ensemble. It's not a very
I don't
coarse
think, I mean,
thing.
going to the micro state really is where, I mean, that this picture will lead to that, right? Because this is already averaged. So it's not clear what this question.
But in n equals 4, so
Yeah.
just go back to Sandeep's question. In n equals 4, you have a similar picture. Let's say you've got the ingoing Hawking modes.
Yeah.
And then Sandeep's asking, can we find what linear combination of the ingoing Hawking modes are the orthogonal states? Is the answer to that yes?
Yeah,
That sounds very surprising.
It'll be some, I guess you can express it as some complicated superposition over these geometries at least. These operator insertions behind the horizon, as we said, once we've got a overcomplete faces, then we can express some particular microstate as a superposition over those. But it's some very formal thing, right? Where we're just expressing something as a linear superposition over different geometries. It's not clear what the geometric, like if someone falls in, what do they experience? So that's the thing that's unclear.
I see, but it will tell you what the true. I mean, in effective field theory, inside,
Yeah.
there are many more states because they're all the Hawking modes.
Yes.
It will tell you that this state is actually secretly that.
Yes. It should in principle tell you that. Yes.
I suppose you can calculate overlap.
Yeah.
Between
Yes.
Yeah. You can calculate what are called null states, like the secretly two states which are the same.
So it sounds very. I mean, if one could actually do something.
Yeah, I mean, in practice, it's probably really, really
The
hard.
claim seems to be that it can be computed according to Vijay and so on.
sorry, how exactly
No,
this
if
n
we
product
just-
matrix is being computed?
Sorry.
How is this n product matrix is computed in n equals 4?
The inner product matrix, just using the path integral. Like you can like similar to how we computed psi Sij, you can compute all moments of psi Sij. Just using the path integral.
Moments of psi Sij.
More like psi Sij to the n, etc.
But I thought we are not doing any ensemble average, right? Just n equals 4 we are talking about.
Doesn't matter. Like we're okay.
Well, so
If you had the full path integral exactly, then you could have just computed one thing and be done with it. The gravitational path integral includes wormholes, and so it's averaging over something. It's not clear what.
Yeah, when I was talking about this average in Shiraz said, let's look at n equals 4. So there also it's not clear to me that you solve the issue.
I see.
Yeah, I mean, if there was a
Who looks at some average states like this in n equals 4, I thought that's what.
No, but n equals 4 might as well be an ensemble average theory, right?
Yeah, let's see. I just.
No, I'm saying the theory, the Lagrangian is not ensemble average, but the states are.
No, I was thinking you look at the ingoing Hawking modes. So they're very particular states. You use those. And then Abhijit's point I thought was that, okay, if you try to compute an inner product, you'll find psi ij square is not Sine
Yes,
square.
yes.
So you've not got a sensible answer.
Yes, yes. So if you've once figured out what the sensible gravitational path integral 2 into n equals 4 is, then we could ask this question. But I mean, as long as you have wormholes, then there's some averaging and we don't know what that means.
So it's
But
not a self-consistent thing.
But if you assume there's an ensemble, then you can compute all moments, get the answer from that, and you compute this answer. So that's consistent with JT being an ensemble, etc.
Yeah.
In n equals 4, how to interpret that is unclear because we don't think there's some averaging, at least at the level of the theory. Yeah. So for psi Sij, we have these boundary conditions. And so we're going to do something very similar for psi Sij squared. And you might think if psi Sij is, let's say if I and j are different, psi Sij is 0, psi Sij squared should also be 0. And what the gravitational path integral tells you is that there's some additional contribution to this. We'll try to make sense of that. The additional contribution looks like this. It's basically these two boundaries that we had, which was of length beta. Those are these two boundaries. And then there's some ring that sits here. And it's filled in with a wormhole geometry. So this, so let's say there was I and J. I, J. Then similarly, there's I and J here. So what we see is that there's these two different boundaries, and there's a possibility of having this connected geometry. So it's I, J. For any choice of I and J, there's a possibility of having this geometry which connects between these two different boundaries. Because initially what we were missing was if you started with a brane of flavor I and the only other boundary condition is a brane of flavor J, there's no way to connect them, so there's no geometry that contributes to this. But now when I compute this square, there's another I that's sitting on the other boundary. So there's a possibility of getting this contribution which connects them. Right? So that's this contribution. This contribution is topologically suppressed. So in this theory, there's a large parameter S0, and this thing goes like e to the minus S0, but independent of I and J. No matter what I and J is, there's this. Okay. So this is already some sort of contradiction, right? So psi Sij being 0 and psi Sij squared being non-zero. And the way to make sense of this in this theory is that there's some averaging that's happening. As we said, the state psi itself was defined by some average over random numbers. So when we do an average, it's possible that the average of the inner product is different from the, it could be 0 and still the average square could be non-zero because there's some variance. Right? So
just out of curiosity, is the average over the Hamiltonians important for this in the SSS model? In fact, the states, and just because CIJs are average.
It is important because it will give you the gravity part of the answer. So there's some, the contribution that's coming from the gravity part, we care about that averaging, and the number of flavors we care about the brain. Okay, so since we're averaging over these C's, it's very possible. So roughly speaking, the way to visualize it is psi I, psi j is some random number. So the overlap between psi I, psi j is some random number, which as you change members of the ensemble or this choice of random numbers and so on, it's just pointing in different directions as a complex number. But when you square it, it's a positive definite thing, so it can't vanish, it can't just cancel out, and so it's going to give you some non-zero value. So what this is saying is psi Sij should be really thought of as some random number that is small, but random. So that the average is 0, but the variance is 0.
How this S0 is connected to this?
Yeah, so this theory, I should have said this before, S0 is just a parameter in this theory which suppresses higher topologies.
How this S0 is connected to this linear formulation you have written, CIJ?
So in this theory, these EJs have some density of state. So the density of rho of E goes like e to the S0 times some function of E. This e to the S0 is roughly the density of eigenvalues that you have. So the number of EJs that exist. So if you just imagine projecting onto some window of E's, then there's roughly e to the S0 states there. And so it's coming in because of the number of states that are contributing to this calculation. In the bulk, the way it shows up is because of this topological suppression. So this e to the minus S0 is because this thing is topologically suppressed compared to this. Yeah. So the lesson from this, and discuss this a bit, so I'm not going to dwell on it, is this fact that at least at some coarse grain level, so here we've really made sense of it in terms of averaging over some ensemble. It's not so clear what it means in general, but as soon as you make some kind of coarse graining, some sort of averaging, then you can make sense of the fact that these answers are different. What detailed coarse graining we do depends on
And the
details.
fact that you just said that this coefficient does not depend on the how many ij you are inserting. Does it have it? Why this? Is it just a calculation you do, or does it have any?
Oh, the fact that this doesn't care about ij. It's because what we said here was the only thing that was important about ij is if I and j are not the same, then there is no brain connection. If I and j are the same, then there is a brain connection. There's some action coming with it, but that's it. The I and j is just some global, like some flavor label that's being carried. There's no other dynamics to it. Here, because we computed psi xij squared, there is this contribution which sets I equals j. Sorry, I equals I and j equals j. And so it doesn't matter what I and j are, you can always draw this diagram.
Sorry, Pratik, the analogous thing which is confusing me in this set of work. So let me ask you here. Since the SSS matrix model is in the double scale, right?
Yeah.
The parameter which counts topology is S0, which is different from the rank of the matrix, which actually goes to infinity, right?
Yeah.
In the double scale.
Yeah.
So the number of states in terms of the dimension of the Hilbert space that you can construct is actually infinite, right? In the double scale limit.
Yeah.
So why is it that the number of states you will be able to count here is governed by S0? If I were just constructing the matrix model, I would get an infinite number of states.
Not so what we're doing here is looking at the canonical ensemble, right? So there's still a Boltzmann suppression for high energy states. So it's roughly going to be peaked at some set of energy states. So it's just picking out the number of states there, which is fine.
So the temperature of the temperature goes in. Yes, because this is just a matrix model.
So even in the double scaling level, the local density of states in a given ensemble is fine.
So the energy range becomes infinite.
Yeah, the energy range becomes infinite. So if you really compute the rank of the full thing, then it's infinite. But if you're computing something like partition function, then it only cares about some finite set of. Okay. So good. So this was okay. And so if you follow this calculation, similarly, so the fact here that was important was that there was these non-trivial overlaps between these different states. And the gravitational path integral is seeing that from this calculation. This is basically the same mechanism that gives you the page curve. So in the page curve, the confusion obviously was that there was a large amount of entanglement between the interior and the exterior. There were probably more than e to the a over 4g number of states in the interior that were entangled with the outside. There were more modes. But this similar flavor of calculation would tell you that all those states that you thought were different weren't actually that different. And they actually still can be compressed into a subspace of rank e to the a over 4g. So the maximum entanglement you can have with it is still just a over 4g. It's not the thing that the Hawking answer would suggest.
So this would suggest that you cut off the interior. Is that the model that you cut off the interior so that you don't have that bags of gold at all?
No, it's not. It's actually embracing bags of gold. It's saying that bags of gold are fine because it's just an over complete basis. Different bags of gold. So let me just draw a picture for a bag of gold. Bags of gold are roughly speaking geometries where, I mean, you have some sort of horizon, but then there's some big geometry behind it, which just caps off. So there's no other boundary. It's just a one-sided black hole state where the outside just looks like a regular black hole, but then there's a huge interior where you can have like a whole universe, you can have all sorts of things. This in the interior can have a huge amount of entropy, which can vastly exceed the Bekenstein-Hawking entropy. So often I think what was said in the past was these states are sick in some way, like you can't have these states and so on, because you want something to be consistent with the Bekenstein-Hawking entropy, so you don't want that many states there. Now, what is being said?
Produce them from actual collapse. Right?
Yeah, I mean,
the
argument was, exactly. But now the claim is, even if you could construct such states, imagine you had different states with some spins in some different directions or something. You can construct a different configuration of spins, which naively is orthogonal because you just flip the spins, for example. But you can do a similar kind of calculation where you'd find that psi I psi j would be 0 because obviously semi-classically you flip things. But when you compute psi I psi j squared, there's going to be a wormhole contribution to that. That thing is going to tell you that what you thought were orthogonal states actually have some small overlap with each other, which is very hard to capture using the gravitational path integral in detail, but you can estimate the magnitude using the psi I j squared calculation. Then from that and then further processing, you can estimate that the number of states is still consistent with e to the evaporation. So no matter how many bag of gold type states you have, you never run into this issue because all of those are secretly slightly overlapping with each other, and so it's still consistent with e to the. That's the yeah.
If we had a second side for n equals 4, then you really have lots of other states on the other side.
Yes.
What goes wrong with? So you shouldn't be concluding there that the if you did the calculation on this side that all those states were overcomplete.
So this wormhole really was allowed because we had only one boundary. If we had two boundaries, then there's no analog of this wormhole.
Nice.
Yes.
So just to understand, the point is not so much that you're cutting off the geometry, it's that you have this label I.
Yeah.
And that label I taking infinite number of values or whatever.
That's right. That's the
important analog of the bags of gold,
yes,
but it's actually cut.
That's right. That's the important.
And within this theory, is it clear that if I do a Lorentzian continuation of this corrected geometry, then a singularity will appear?
Oh, in this theory, actually, there's not a singularity. Like JD, in that sense, is kind of too simplistic because it just has like some.
So you can declare the dilaton becoming smaller.
Yeah, dilaton. So in the conventional sense, the geometry is just hyperbolic space. So there's nothing going wrong with that. But then you can look at the dilaton. If you had a matter field on it, for example, then there would be something to see from that. So morally speaking, yes, there's going to be a singularity in the future.
Even in this corrected.
In this geometry? Oh, you want to analytically continue this? This one, yeah, I think it'll still have a. This one will basically look something like the thermofield, but a long version.
It has a different boundary condition for preparing that state.
Yeah, it'll. I mean, if you analytically continue it, it'll look something like a long wormhole, where the matter is somewhere deep inside. But I mean, it's not on this slice, so you won't really see it in the Lorentzian space. So just this slice will just look like this with some exteriors here and then some long wormhole.
So if you just see from one side, you see a black hole.
Yeah.
You can't really say how many states were inside because it could go up to another bound.
Correct.
But you can say how many states are accessible to you somehow. How many states you could entangle with?
How many states you could entangle with? Yes. Yes.
So
yes.
The other stuff are out of reach.
Yes.
As far as you can see.
Yes. Good. So the point here was of this thing of somehow the effective field theory sees things as orthogonal, but in the fundamental theory, they're not really orthogonal. That's sort of one interpretation of what's going on here. And this is, if we can think of this as another refined version of complementarity. So yesterday we had these two versions of complementarity. Let me mention another one, which is based on what we just said. The idea is we just think about, so in the version of complementarity that we discussed yesterday, we were focusing very much on observers, right? We were talking about trying to describe the causal patch of a single observer and trying to take that maximally seriously. And we were trying to say that quantum field theory and curved spacetime should not be taken literally.
Really sorry. Make sure I understand because I mean, the correspondence between the SSS matrix model and JT gravity is not the JT gravity theory is two-dimensional, but the SSS matrix model is not a quantum mechanics, right? It's just a matrix integral.
Yes.
It's not a conventional hologram, right? It's not one dimension less. It's just a matrix integral.
I mean, it's a 0+1 theory.
It's not a 0+1, it's just a matrix, right?
Yeah, that's the Hamiltonian.
Yeah, but I'm just saying.
I mean, it's not a 0+1 matrix quantum mechanics, but it's still a 0+1 dimensional theory.
Yeah, you declare that. So I guess is the correspondence supposed to be that states correspond to states? I mean, is that the
states?
I mean, in standard AdS CFT states correspond.
States correspond to states. Yeah.
The way in which it's an unconventional is a normal holography or any old-fashioned holography. You write out a Lagrangian for the thing.
Yes.
Yeah, you just say this is the answer.
Yeah, this is the answer. This is the answer of the ideal states. Yeah. That's right. So I agree. Okay, you have the Hamiltonian. You have the matrix model which tells you the distribution of eigenvalues of the final Hamiltonian.
That's what you mean. Yeah.
So it's a little unconventional, but okay. States are still states. Because that's going in here, right? So I just wanted to make sure.
Okay. So now in this modified version of complementarity, we're trying to again try to take quantum field theory on curved spacetime seriously. So the downside of complementarity in some way was that we had to try to describe specific physics of a causal patch and so on, and it was difficult how to concretely make sense of that within quantum field theory of on curved spacetime or some sort of formalism like that. Here, the advantage is that we can just go back to quantum field theory and curved spacetime as we understand it with some new rules. So this star is going to be some additional rules related to what we just discussed, which nevertheless tries to make sense of using quantum field theory and curved spacetime as a formalism we can use to try to make predictions for what happens in the true quantum gravity. So one way to think about it is to think about the map from the effective theory to the fundamental theories. Some map from the Hilbert space, effective field theories, to the fundamental theory. Okay. And in the special case where we talk about, say, black hole evaporation, then this effective field theory can include the black hole interior, like the whole black hole interior, which can be really big, and at late times when that can have more modes than the Bekenstein-Hawking entropy. So let's say this is some e to the s effective dimensional space. This is getting mapped to a space which we think is e to the s black hole or e to the a over 4 dimension. So this is what's called a non-isometric code. So this is a code which is going from a larger space to a smaller space. So there's no possibility of trying to preserve inner products. If you map inner products here, which are say orthogonal, they can be slightly non-orthogonal. I mean, they have to be slightly non-orthogonal in that smaller space.
So why was that large again?
And this is large, so we can consider situations where it's large. So the situation where it's large is when you have a black hole at late times, right? So black hole at late times, then this slice can be very big. It can have a lot of modes, which would be entangled with this stuff. And the corresponding area is really small. So if we just talk about this part of it, then, so this map is just talking about the black hole part of it. So there we have an effective field theory degrees of freedom, which is larger. Okay. And then there's an e to the over 4g, which is the final.
Ingoing Hawking modes. There are more ingoing Hawking modes than remaining entropy of the black hole.
Yes.
And the partner ones. The partner ones.
What was it? Partner.
Normally we would call this.
I was thinking,
That's right, partner.
The outgoing but interior.
Interior.
Yeah. We know sort of by definition that past the page time, there's more entropy those than the black hole.
Exactly. So past the page time, you reach this point when this has become a non-isometric type map, where inner products here are not faithfully represented on the fundamental. Okay. So now, within this formalism, you can ask what is the inner product that's relevant for an interior observer, right? So for an interior observer, there's some prediction you get from the EFT, and there's some different prediction you get from the fundamental theory. For example, in this bag of gold type state, you have this huge interior, and there's a tiny A over 4G associated to it. So this could be a huge cosmology where you just have some person living there who's just happily doing measurements and so on. One guess would be that the inner product there should be perfectly consistent with effective field theory. Nothing is going wrong in this person's description. It's just that there happens to be a singularity in their future and past, maybe, but that's fine. Like there's a singularity in our past. So here, one guess might be that the effective field theory inner product is the relevant one. Another guess might be that the fundamental one is the relevant one because we think AdS CFT is the supreme thing. Like it's telling us exactly how to compute things, and that's how that's the inner product. That's the well-defined inner product which we should use to compute things. Okay. So one
That's confusing for me
Yeah.
because AdS CFT doesn't describe the interior directly.
That's one way to think about it. I mean, I'm not sure everyone would agree on that point. I mean, that's one way. That's one perspective, which I think is pretty reasonable. If you believe that AdS CFT only describes the exterior, then you would say that the effective field theory in a product can be relevant for the interior, and it's perfectly fine.
I'm not saying I'm pushing that. I'm just saying.
Yeah. No, you could say that. I'm here taking AdS CFT maximally seriously and saying that all inner products you can compute should be computed in some fundamental quantum gravity theory.
Yeah.
Then you would be forced to the conclusion that it's the H fundamental inner product that you should take seriously. And then we can see what the consequences of that.
But I thought the general thrust here is that that math slice that you've drawn, it's got low curvatures everywhere.
Yeah.
There are a huge number of states inside. If you did standard quantization of say some quantum field in curved spacetime, you have a very large number of states, but you went wrong because whatever, some quantum gravity effects.
Yeah, exactly.
Either the
wormhole type effects would be important.
Which are going to, right?
That would be what you're trying to say. So in this context, one interesting thing that came out of some discussions, partly in a paper by Kim, Preskill, and Tang, and another paper by Akers, Engelhardt, Pennington, Harlow, and Vardhan.
So the idea is that this why the quantum gravity effects? The reason the quantum, you say these words because this geometry begin with is subleading.
No, it could be leading, like that geometry is leading.
Okay, so if I'm a person there doing measurements and so on, so I'm not finding inner product non-zero, zero, right? I mean non-zero, right?
I don't know. Maybe depends. Like it depends on what's the relevant inner product. That's
yeah.
Like if I'm an interior person and I just flip a bit and I try to compute some sort of interference experiment where I'm trying to test whether these two are orthogonal or not. One reasonable way to say it would be there seems to be nothing wrong there. There's no large curvatures, etc. So they should of course be orthogonal, and HEFT should be the correct answer. Another thing could be to say the only way we know how to compute this correctly, including quantum gravity effects, is to compute
But
this.
what quantum gravity? I'm just a macroscopic observer doing it.
Well, whatever you do has to be embedded in the theory of quantum gravity, right? Otherwise, what are we doing?
No, I mean the regime where those effects for me should be.
We think so. We think so. But I mean, these wormhole effects seem to be large. I mean, if you care about these wormhole effects giving you the page curve, then you should care about this as well. It's the same physics.
Already complementarity.
Yeah.
You would have thought.
Yeah.
Yes,
Yeah.
okay.
Yeah. Same.
Sorry.
Already in the complementarity story, you had a nice slice.
Nice slice.
Yeah.
And there already we have.
Okay. No, but as a local person, right? There the issue was.
So there you added in this physics of local person.
But as a local person, I should be getting the right inner products.
Good. Yeah, it depends on what right is. Like it could be that there's some quantum gravity effect we're not accounting for. It would be a failure of effective field theory for sure. But we know effective field theory is failing anyway. It's not giving you the page curve. So it's not crazy to believe. I mean, like it's one possible perspective to say that the relevant inner product is.
Maybe corrections are exponentially. Right?
I'm just going to say that.
Yeah.
And maybe this local person's going to die before they can measure things with enough accuracy.
Okay, that is a perspective which I'm not sure is necessarily true because the same sort of issues we'll see will arise in closed universes, etc., where there doesn't seem to be a bound on how long someone can live. Like they can live pretty long, and I don't see an obstruction to them doing these experiments. It would be an interesting thing if the way out from all of this is that someone just can't physically do this experiment, but I don't see how that's the case. It would be a complementarity type argument where it's like you can't do this, so it's fine.
Where is the observer of H fundamental?
No, so we're forgetting about observer. That's the important point of complementarity double star, which is in complementarity and complementarity star. These are all names I came up with. We focused on the physics of an observer. So I had to tell you which observer. Now I'm saying forget about that. Just talk about the QT on curved spacetime description. There's some map between them. That's what's being discussed. The only place where the observer is showing up is when we ask what is the relevant inner product for that observer. So it's perfectly clear that for an exterior observer, H fundamental is most definitely the correct inner product. Like whatever they will measure will almost definitely be consistent with that, just like standard AdS CFT, because near boundary observers like the boundary observer. So that inner product seems fine. The question is, what's the relevant inner product for the interior observer? For the interior observer, it could be HEFT or H fundamental. There's good reasons to argue for both. Because HEFT, because it's just a huge space with no seemingly big quantum gravity effects, so you might think HEFT is the relevant one. H fundamental, because we think AdS CFT may describe everything. Like it's a complete description of physics in the world.
I thought the moral coming out of this is that quantum field theory on, in a semi-classical sense on given backgrounds breaks down because you have to consider other topologies.
That could be, it's still going to be.
Trying to do it like this, but you have those other, if you're trying to precisely count the dimension, you have to account for those other.
Yeah, but it's still going to be a very, very drastic failure of effective field theory.
The inner products change slightly, but you have states. No,
not so slightly, yeah. So we can talk about how slightly
I
it
thought you
changes.
would say e to the minus.
I was going to say that, but then we'll talk about why that's not good enough. Yeah. So let me just say that.
So if I fall in, in the black hole, and I'm doing whatever, and then the black hole is evaporating.
Yeah.
Then I think before I hit the singularity, the person should burn up, I think. Because the Hilbert space is decreasing, right? I don't think why does it matter whether I have my degrees of freedom, the orthogonality has gone. Why is there an orthogonality to begin with? Because all of this is being encoded by a smaller Hilbert space, right?
Well, that's definitely relevant for the exterior observer, but what the idea of complementarity was that can be perfectly consistent with a smooth description of this infalling observer.
But if there is no enough Hilbert space there, how can this?
Which Hilbert space? Like it's there's a fundamental Hilbert space which is relevant for describing exterior physics. If you stay outside the black hole and compute
that's
perfectly
that is the Hilbert space.
Well, that's one perspective. No, it's not so clear. That's one perspective. That would be the perspective where you say AdS CFT is a complete description of bulk physics, and that's that. Then it would be the only inner product to talk about, and then yes, then the person would burn up before they do anything because Hilbert space is tiny. Yes. But that's pretty violent because you can have situations like this where it's a gigantic universe. Like we could be in that right now, and we would like effective field theory would be totally.
So then the outside observer only gets access to a part of it. Is that the viewpoint?
So the point here is So I'm going to propose like two ways of thinking about it. One way of thinking about it would be that the interior still can have some degrees of freedom. It's just that from the exterior perspective, many of them are secretly overlapping. And so as seen from outside, it's perfectly consistent with getting unitarity. So we are getting this page curve back. But it's not like, the interior observer can try to measure, say, overlaps between bit flips and so on. And at least there's no physical contradiction between those being slightly overlapping states as seen by the exterior observer, and them being exactly orthogonal states as seen by the infalling observer, just in the spirit of complementarity because they can't communicate with each other.
But it could be so. As far as I'm understanding that experience of a fallen person, we don't know what happened.
We don't know what happens. Yeah. So we're trying to decide what's the right description of physics for that for infalling person.
No, but there is no principle which will let us do that. What I'm saying also can equally be valid, right?
Yeah, we can come up with some rules and see what's more reasonable. In AdS CFT as well, we have to come up with some dictionary, right? This is basically the issue of having a dictionary for the interior. Like, how do we describe bulk physics?
But is there no way to answer this from AdS using AdS CFT? I thought
it's a dictionary issue. So it's going to be like we will have
to find some two-sided black hole. Can we not use that? Because two-sided everything we access.
Yeah, that also is not so clear. Okay. In this perspective, where you really take seriously that the CFT inner product is all there is, then even in a two-sided black hole, you'll see large corrections for relevant.
Sorry, I thought that there you said that there would be that the whole calculation would change because the second boundary.
No, but the analog of it would be that you have access to both boundaries. Then you can try to do some experiment, and then there'll be a violation. There's still an inner product that you're defining on both these boundaries. And then, if you have access to both the boundaries, then it's the same as having access to this one boundary. I'm just saying that given access to both boundaries, you still don't know what happens inside. Yeah.
It's one way to think about this that the HEFT is like the larger, is some description of the n going to infinity limit of the function.
Yeah, so if you say that, then I think in mind you see this, you secretly mean that so in our universe maybe we have some finite value of n, and then it's H fundamental that's relevant for us. So one way of saying that would be H fundamental is the relevant inner product.
And then HEFT is like some
Some approximation to this, which is completely irrelevant in this limit. Which could be completely irrelevant in some.
Yeah, but you'd like to say that the corrections are only very small in the n going to infinity.
Well, not quite. Depends on the
something.
I would same thing, they should be E to the 1 over G nu.
Yeah. You could say that,
He
but
somehow seems to say they're bigger, which is worrisome. I mean,
that is precisely why this paper got so much mileage because of that. That it's exactly that one. Because we shouldn't be so comfortable. People said that e to the minus 1 over g, and I think that's too quick. It's because of this bag of gold thing that you said. It's exactly because of this. So, yeah.
So we could be in a evaporating black hole.
I'd like to think so, yeah.
what is this?
So we could be currently in an evaporating, I mean, later.
Yeah.
Yeah, we could be inside.
Yeah. I mean, so
There is
it's
no-
interesting that
there is
We probably just crossed the horizon as we were talking.
No, not
this is
necessarily.
a-
So there is no way we can see that it is the black hole that we are in is evaporating and we are also gonna evaporate and so on.
Should we see that? Yeah.
There's no, that's why it's such a big paradox, right?
Yeah. I mean,
No,
it's
this is
interesting
like
because
outside the paradox, right? This is really where this is the question about the fallen off.
No, but I mean, we are.
No, that is the
we
paradox. The paradox is
Nothing
because of the
else.
infalling observer. If there's no infalling observer, there's no paradox.
I mean, CERN could be operating inside the horizon.
Yeah.
You know.
Yeah.
Might well
That
be.
is the issue.
Might well be.
That's what I mean. Which paradox? There's a new paradox. The standard information paradox is
Standard information paradox also, you could just not care about the interior and then it's perfectly fine. You just have some sort of stretched horizon sitting there which like radiates out. You could say there's some UV thing happening there and then it's perfectly fine. There's no contradiction with our experience.
No, I mean,
Unless you're
island-
falling through it, right?
the island stuff is also island is supposed to kind of tell us the question to that answer to that question. Right?
It's not a complete answer. I would say it gives us some direction. I don't think it gives a complete answer.
But I mean, if you were in the bulk, you wouldn't be able to tell here is where the island lies. Can you? I mean, what's the local diagnosis?
We talked about hitting the island and burning up. Right?
Oh,
Did
as
we-
you're moving in the interior.
If someone acts with a complicated
Yeah.
operator, yeah.
No.
Yeah.
But I'm saying, if you're an interior observer, you're going along. You're not going to tell here I'm crossing over into the island. It's all.
The outside guy has not done some crazy experiment.
Yeah, let's say the outside guy doesn't do anything. I'm not going to be able to know where is the island, where is
Yeah, it's a very non-local.
yeah.
I mean, there could be some very far off person who's entangled with some region and that can give them an island which you won't be able to see locally. That's true.
And
Yeah.
so the statement is that the H effective observer will calculate psi I psi j mod square and he will get equal to 0, but
Yes.
H fundamental will get irrespective.
Correct. So let me just get to that point. So this point that was being made is that for some purposes, it doesn't matter which one we talk about, which inner product we talk about. So just as you said, like if you compute inner products in HEFT, you can have perfectly orthogonal states. Psi Sij is exactly 0. But when you compute it in H fundamental, because of this projection down to a smaller space, they'll have some e to the minus s naught type, e to the minus a over 4g type overlap with some erratic phase or something like that. Some very detailed answer, which is hard to compute from the gravitational path integral. But they would be like close at least. So if it's slightly, if it's exactly orthogonal in HEFT, in this situation I'll just discuss, it'll be close in H fundamental.
This error is entanglement error, or is it due to the
It's going to be related to the size of H fundamental. So here's the statement. The statement is basically that so we can model this V in a particular way. It's usually modeled as some sort of generic random map from HEFT to H fundamental. In fact, if you look at the JT gravity model, like there we have an explicit description of what the states are. It's basically that map. So this thing that I wrote down, which was a random superposition over energy eigenstates. That energy eigenstates has some e to the over 4g type dimension, which is this H fundamental. And then the number of random coefficients I can have can be really large. Okay, so you can have those set of states. And then the map is basically what we wrote down. Psi I is just given by that random superposition. Okay. So if we have this situation, the thing that was shown was that basically V preserves inner products. With errors order e to the minus a over 4b. So in the case of black hole evaporation, here, as long as we don't go to Planckian sizes, we have some nice slice where this area, some finite value, it can be small, but it's some order 1 value. Then this thing is some e to the minus 1 over g suppressed thing, as Sandeep was pointing.
4 typical states.
For
If you choose states on the random.
Good.
Because clearly there are states which will.
Very good. So the statement really is this for typical states in HEFT. Just for typical states in HEFT. Yeah.
Because you could clearly choose states that are also
specific states.
Where the ideas order one.
Exactly. Like you can pick null states, which are basically 2 states in HEFT which secretly map to the same state in H1. Yeah. That's all. Very good. Yeah. So, but the expectation here. So here's the seemingly consistent story that was said in this paper of non-isometric, which is those states are very complicated. They don't have a good gravity description. These null states that you're talking about, for all the states that are relevant for effective field theory, like the usual states we can consider with simple operations that are acting on these bits in the interior, then we can consider some class of states, which they call simple states. And the only motivation for this simple here was the Harlow-Hayden complexity bound criteria. Really what goes into the calculation is that for any small set of states, you can encode them approximately orthogonally. So roughly speaking, if you have E to the S dimensional Hilbert space, then roughly speaking, e to the S approximately orthogonal states exist there. So if you have exactly e to the S orthogonal states, there's approximately e to the S approximately orthogonal states. Like if you just think about bits, then you can have just random coefficients on them, and many of them, just like a random walk, will almost all cancel. So in norm, the overlap is going to be pretty small.
It's just the dimension of the sphere of that length.
Yeah, exactly.
Right? I think then you have some small.
It's just the volume of Hilbert space grows very fast with the dimension, and so it's really big. So you can fit in a lot of approximately orthogonal states. That was really the idea. And then, once you have that, then you can just choose some appropriate set, which is appropriately small. And then any such set, you can preserve their inner products to good accuracy. To accuracy controlled by e to the minus a over 4g. Okay. They tried to say that the simple states were the relevant ones because of this Harlow-Hayden criteria, but that's not so right.
Who's they, by the way?
They is Wilkers, Engelhardt, Shreya, Jeff Pennington, Harlow, that way.
We had 3 lectures for
right. Yes. Because you also mentioned Preskill, Kim.
Actually, Kim, Preskill, Tang was a paper that came even before this. It's somehow underappreciated a little bit.
They talk about pseudo-randoms.
Yeah, so they made a big deal about this map. I mean, it's very unphysical from a quantum information perspective to have a random map. Like a random thing is very complex. And it's very hard to imagine physical processes which would give you something exactly random. But you can have these pseudo-random maps, which basically were the math is almost, for all of these purposes, it's exactly the same as a random map. So you just have that pseudo-random map. There's some assumptions you need to make for when such maps exist. But once you have that, then you have a map which is actually easy to simulate, but nevertheless, it will give you all the properties that you want. So it's a more physical version of it.
And somehow this notion of a typical state maps to, is that the map? Like here you were saying, if you take typical state, if I understood you right, you take typical states, then, they look approximately orthogonal, but not quite. I thought that was what was
something like that will still be true for pseudo-random.
And then those typical states map to pseudo-random. Is that roughly?
Yeah. Instead of having a random projection, you have a pseudo-random projection.
Which is like a typical state.
Yeah.
May not be.
Yeah. So it really makes almost no difference. So it's all, that paper was already, it had all these ideas. It's already there. Okay.
Some of the complexity criterion was slightly better on a better footing.
Yeah, I think because it was pseudo-random, it was sort of more natural to put in complexity criteria because the physical thing to simulate and then makes more sense. Yeah, once you have a random map, then basically any set would have worked, and then they just put in simple. Like really, there was no reason to put in simple. That's good. And the same sort of idea works for observables. Same sort of thing for observables. In the sense that as long as you have observables computed on simple states, so if you have simple operations, then that preserves the effective field theory. So this is in consistency with the Harlow-Hayden type criteria, where you say that you have simple operations and that preserves your effective field theory. Otherwise, if you act with something that's too complex, then you spoil this relation. And so what's going to happen is if you act with such an operator, there's no obvious bulk description of that in terms of an effective field theory description. So it can break causality. And the third thing was that this keeps in the page curve, which is sort of obvious. Which is just the fact that once you compress down, so it will give you like the generic state will have entropy that's given by this A over 4G. And so it's going to be just that. Okay. Just some things to say about this. An interpretation of this map. So this paper tried to make a big deal about this just being a map at the level of HEFT getting mapped to H fundamental. In physics, it's quite similar to an idea that was discussed yesterday, which is the final state projection. So this is this Horowitz-Mandelsena proposal.
So just referring to that,
Yeah.
so I mean, so far what you've said is that look, I could just in general, if I have a big enough dimension, Hilbert space construct the analog of effective field theory states, right? And then it is a fact that simple observables or whatever will be computed quite precisely whether you work in the effective description.
Yeah, exactly.
Taking
So,
to be
so this question
versus the exact description.
So the question we discussed about which inner product is irrelevant in such scenarios because it doesn't matter, they're almost the same anyway. So that's okay. Okay. And just to say, like, so this Horowitz-Mandelsena final state proposal came much before Islands and sort of 2004 or something, where the idea was one way to get the information out is to have a sort of so the thing they noticed was that there's a singularity here, right? So we should pay attention to the physics of the singularity. And the idea was, so here what's happening? So we have a map which goes from the effective field theory to the fundamental description, which is a sort of a projection. So you have some large state and then you project onto some definite set of states, which is rank bounded. And the same idea was there in this Horowitz-Mandelsena proposal, where instead of talking about intermediate times, they just talked about the end of evaporation. At the end of evaporation, what you want is that it should be projected onto a definite state because A is just 0 at this point. And so there's a one state that's being projected onto. So all effective field theory states should get mapped to this one state. That is the idea of this post-selection. So what they were saying was, since there's a singularity here, their idea came a little bit from cosmology. In cosmology, what we try to say is that there's something special about our initial conditions, right? So there's some particularly nice state that we are beginning from. And their intuitive motivation was, if we have something like that for an in state, why not one for an out state as well? So why this is just saying that there's a special state in the past breaks time symmetry. And so you may want that in the fundamental theory of quantum gravity, every singularity has an associated projection. And so then you would be supposed to conclude that there's a final state projection that's happening so that there's a very definite state at the singularity.
Which means that the interior has a unique state.
Yes.
So it's different from what we've been saying so far.
It's not that different because so in the spirit where you say that H fundamental is the right inner product, there it's exactly the same as this. Like what we said so far was an intermediate version of it where we stop at this point. Right? Like we only have some part of the interior that we're focusing on. that is consistent with the slightly larger Hilbert space. So the statement is there's still a singularity there. It's just projecting you onto a Hilbert space that is e to the a over 4g dimensional. And
you're saying that at that point, the Hilbert space dimension is
like
equal to 0.
Exactly. So it just keeps progressively decreasing until you go to 0 at the end.
That is not, isn't it like hitting the singularity in a continuous sense?
Yeah.
So that means I should feel that.
Sorry, what is I didn't understand.
As a person is falling in,
Yeah.
we agree that if the person hits the singularity, then it's done, right?
Yeah.
When you finish there,
Yeah,
it's
yeah.
a single state.
Yeah.
But we are already encountering analog of that phenomena earlier and earlier.
So the
And slowly that Hilbert space is going to 0, right?
The confusing thing.
Why is there such a drastic change in experience? That I'm not burning up slowly. Rather
Sorry,
than.
I think I did something.
So I'm just
So
trying
there's a
to
singularity
see
in the future.
the
have
some
some
space that I have access to as I fall in.
So we have some observer, let's say, who fell in this way.
Yeah.
And then, okay, now.
Yeah, I was saying that Hilbert space,
Yeah.
even though I see all these infalling Hawking modes, etc., which
Yeah.
may look like I have a big Hilbert space.
Yeah.
Actually, Hilbert space is going down and down and down, going to 0 all the way.
In the fundamental picture, yeah.
In the fundamental picture.
Yeah.
But as I hit the singularity, there is clearly a change in my experience. I mean,
Yeah.
you also want to say that there is complementarity and then there is no singularity.
No, at the singularity, of course, if TFT has to break down because there's large curvature. So there is
exactly.
no problem
So
there.
there is no problem,
Yeah.
right? But now we see a kind of a continuous analog of the same phenomena in the sense that one way to say that my experience should be different is that there's large curvatures.
Correct.
And the other way is to say that there is final state quantum mechanics, the final state prediction.
Correct.
But there is also projection to rank 2, rank 3, rank 4, and so
Correct.
on, subspaces as I go down and down.
Correct.
So I was thinking that this is an experience of burning up.
I mean, it should certainly affect your physics in some sense.
No, burning up. This is
It's not going to be burning up. Like,
why is this not just the continuation of the same picture?
I mean, it's not that continuous. Like, this thing is pretty drastic. As we saw, like, corrections to the inner product is exponentially small. So even if you have like 10 bits, it's like a tiny correction to your inner product. So it's really going to be really at the end that you burn up. It's not that continuous. I mean, it's continuous, but it's like very fast towards the end.
But because of that exponential factor.
Because of the exponential.
But it's just an order 1 kind of thing, it would.
Yeah, I mean, yeah, that point you should say is
I'm seeing the fact that my Hilbert space is becoming smaller.
So this.
Before hitting the singularity.
Correct, absolutely.
But order 1 would be blank curvatures.
Yeah.
So even in the classical theory.
Yeah.
I mean, the confusing thing about it is that this thing is supposed to be a description of physics in this entire time. And of course, that also includes all of these slices, which are perfectly smooth. It's like really far from.
Yeah, that's what I was going to say.
yeah.
That to associate a particular slice with the end,
Yeah.
you can do it many ways.
Exactly.
Right?
So there's a
So,
big discrepancy in that. Yeah, that's right. That's right.
Yeah.
So one thing that this model misses is diffeomorphism invariance, which is that issue. So you can draw many different slices with the consistent with the same boundary.
Yeah.
That is part of this issue. That is why this is not a complete proposal yet. Final state proposal was only ever talking about what happens right at the end. So it was a proposal for this whole interior, which is a diffeomorphism invariant thing. You can talk about quantum mechanics in that.
But is it saying the whole interior is one dimension?
Yes.
That's different from what you said.
Well, this is some version of that where if you take parts of the interior, that thing is not one dimensional. Like if I just look at the QFT on curved spacetime Hilbert space associated to some fraction of the interior with some non-trivial area on the horizon, that is consistent with the fundamental Hilbert space of e to the over 4g of that area. It's only when I take really the full interior that the Hilbert space
This
vanishes.
is like the complement of the island, right?
Sorry?
Complement of the island.
It's the complement of the it is
The complement of the island that it goes to 0.
drastic.
That is the Hilbert
it's the
space.
boundary of the island. Like, is that what it is? Extreme stuff. It's the boundary. It's the area associated with the boundary. Yeah, it's the boundary. Yes. It's controlled by the boundary.
But then if it was just one state inside,
Yeah.
then I can completely predict what's going to happen inside, right? I mean, it's not like you can do two different things. You could.
So yes.
Did it really mean it just just because finally you had one state
Yeah.
in a evaporating black hole where the area is becoming smaller.
Yeah.
Does that mean that the moment the horizon formed, the state inside will become one-dimensional? That seems quite a drastic statement.
No, what so roughly speaking, so this final state proposal is more concrete than that. It's basically replacing quantum mechanics with a version called final state quantum mechanics, where what you do is you want to so in quantum mechanics you compute things like initial and term operator, like when you want to compute expectation values. The only difference is now instead of this, you also have something like rho final that's inserted in that. So that's effectively doing this projection. You can compute all correlation functions you like. It's just that now you have this extra rule that's put in. Now, one thing that Horowitz and Maldacena tried to argue is that if you're a small enough system, then if this rho final can be a very random looking state. And if you project down to a small system of a random state, it basically looks like the identity. You basically cannot tell the difference between having the projection and not having the projection as long as you're a small enough system. But the global rules of quantum mechanics have completely changed.
No, but is it not saying that you would be in one state as you evolve? Here it looks like depending on your rho initial, you get different answers.
Yeah, you can get different answers. So that's why it's not exactly that statement. It's more like you can start in whatever state you like, and then you sort of project onto that state, and the part of the wave function you picked out, something like that.
So, yeah, this is a continuous process, right? I mean, you are projecting onto a smaller line,
It's not so
then you
clear.
get to zero, right?
I mean, how do you? So
As you say, the area of the island is like that.
But the island is associated with some time for some like faraway observer.
Yeah.
It's not so clear how to associate that time with something for the infalling observer. That's the issue with Cliff invariance, which is there's no. I mean, you can say that once I have some set of radiation here, there's some island associated with that. That seems very relevant for that observer. It's not so clear what that means for this infalling observer. Like if I am this infalling observer at this time, which island do I care about? There's many islands in which I'm concerned.
Yeah.
So which area to talk about? So it's not so clear what the rules are. So this is all when you really try to take seriously that H fundamental is the right answer. You have to address all of these questions. And this is basically an issue with the bulk to boundary map. Like what we don't understand here, we can perfectly well understand the boundary state. Like we can in principle compute the S matrix and all of that. Even if you had access to some computer which would compute everything you wanted in n equals 4, it would be still hard to answer this question because we don't know the dictionary. So it's a separate issue from solving the theory. That's the thing that we're struggling with. And that's the thing that's been left open, I think.
So I mean, that's really the key issue, right?
That is
how do you map the interior to the boundary?
Yeah. The whole issue is the bulk to boundary dictionary. I mean, the spirit of these works was that let's assume that what we get from semi-classical physics is somehow the right dictionary, and then see that it's somehow consistent. So the idea with computing things like this was, okay, somehow if you work with this complexity bound, we don't violate EFT, and the EFT description is perfectly fine. But we see that it is a drastic thing when, firstly, it's confusing how to associate times with the interior. And then we'll also see later how even this is not good enough.
Sorry, just one comment. In AdS CFT, you sometimes encounter the same kind of thing, where it looks like you've got more bulk states than boundary states. For instance, in the giant gravitons.
Correct.
This stringy exclusion principle. And in that context, you really see something dramatic happening in the bulk.
Yeah.
But the gravitons that looked independent actually blow up, become spheres. So you really see it.
Correct.
It's not like it was hidden from you.
Your effective field theory experience should break down.
Yeah. Correct. It sees that fact.
Yeah, it sees it. So you're seeing something very different here, right? Like you don't see it easily. Some very hidden thing.
Sure. So what is, I mean, I know that you have this giant gravitons either because they're rotating or whatever, they blow up, etc. So what was the point that you overcome? Because
naively, you have gravitons, let's say trace Z to the end, that goes all the way to infinity.
Yeah.
But
we know there's a cutoff at N. Okay, so the field theory has told us that. Now you can ask how in the bulk is that it manifested? And it manifests by the graviton becoming larger and larger and larger. No, at some point it no longer fits on the sphere. So it's really very in your face in the bulk.
Right.
It's very different from what you're saying here.
Right.
Somehow that makes me uncomfortable.
Is much more subtle here, let's say. Right?
Yeah, I mean, the only thing we can say which is analogous to that is that there's these wormholes that are showing up. That's the only indication of some new physics, but it's not very much like, it's not like EFT has broken down in some obvious sense, at least. Like you have to still.
Yeah, then it's not shown you.
Yeah, right. I mean, in the situation you're talking about, the bulk to boundary dictionary is very clear, right? Like, we know exactly what the bulk is.
Subtle thing that
Absolutely.
No, but here also it's just at the level of proposal, right? Here at this stage, I could still say that my experience does change as I fall in. I do see less Hilbert space, and then I burn up. Nothing so far what you said contradicts that.
Yeah, I mean, it would
So
just be
I don't think you are arguing for this picture. It's
I'm
just
not
a
arguing for
proposal.
it. I'm just telling you what the
I mean, it's
options
not
are.
like this is
So-
coming from some logical structure.
Let me give you the whole, like the theme of these talks is not to say this is the correct answer. It's to say here are the options. None of them are good. Let's try.
No, I mean, I'm saying the discussion so far also doesn't somehow even lead to that kind of interpretation, right? I mean,
there's not that many options left if we go this route, right? Like you can either say the inner product is H fundamental or H EFT. Like what else do we have?
H fundamental.
Then like
I say H fundamental. There is nothing there, right? I mean, it's just a matter of saying what.
But it's a very dramatic statement. I'll tell you, you can do these thought experiments where you continuously feed a black hole as it evaporates, you know, and then you really sent in any semi-classical sense, a huge amount of stuff compared to S and sign out. And the mismatch can be made arbitrarily long, great, in effective field theory. And if you're going to say that, it's a cut down, I mean, it's quite a drastic statement.
No, but you are also evaporating, right? The black hole is also evaporating as you are sending it.
It's evaporating, and so
how can it be that inside is unaffected? Because there is radiation coming out.
he's sending stuff.
But I agree. But
there's no.
But it's not like
you're going.
they're having a nice.
There is no local effect of the evaporation. You're going through the vacuum. Nice. It's only because the vacuum near the horizon is so different from asymptotic. You see the radiation. But the inside guy just falls in. You have some large universe inside, and yet it's apparently much. I mean, it's quite a dramatic statement. Now, of course, but let me just say, I thought the moral from the first part of it all and what everyone says is that, look, there are small compute the overlap precisely, you have to do some gravitational pathing theater, small corrections, blah, blah. And local physics won't see it, but precise counts will see it. And okay, maybe I'm willing to buy that. You say no.
I think you shouldn't be so quick to buy that.
And so that's what you're saying.
What is the argument?
The argument is
before that I had one question about the giant gun. But there, if you just quantize the gravitational phase space for giant atoms, you see this constraint.
Yes.
You see that just in quantizing classical physics, right?
Yes.
So in that sense, it's very different because here you will not see these constraints.
Yeah, I'm just wondering if. So I'm saying that if you were not very perceptive in the bulk, you didn't realize there were these giant gravitons. You would not have realized you would see them.
No, but you quantize the phase space that you're given, you get what you get.
No, but now you have to realize that there are giant gravitons. If you just quantize the graviton phase space, you would see it.
That's what you're saying.
Like right quantization.
Yeah. Then you have to realize that there's string theory, there are free brains.
I mean, I guess the analog here would be if you knew what the microstates were, like that.
I mean, and it uses the details.
Yeah.
It's not some general kind of blah, blah, blah. Right? It uses the details of the theory. And then once you use that correctly, you see it in your face. This is what I was contrasting with, which is here.
Right. So I mean, we should probably end soon, but let me just make that
hurry is what I'm saying. I mean,
but I think it's a natural stopping point. So let me just say what the issue is roughly, and then we can stop. And partly the issue was what you said for diffeomorphism invariance, which is we want to understand some map that is still consistent with diffeomorphism invariance for the bulk observer. And then the other issue is the fact that the errors were bounded by this A over 4G. So as we discussed, there could be an issue if A goes to 0, like Abhijit was pointing out. Here, there's not an issue because then, A goes to 0 is really the situation where the slice has to cross this corner, right? And that's the corner which these nice slices want to avoid, right? So you don't want to go into that corner. Then you could always say, this thing is really a closed universe. It just has an endpoint which is very singular. So it's some geometry which looks like some rusty thing. This end being single. And so there you would say, okay, maybe we're not in the regime of effective field theory, and so we shouldn't worry that the errors are small. And this is basically what was said.
Why we are not in EF?
We're not in EFT because this geometry on this slice is already singular. Like one part of it, this corner is Planckian, right? So there's Planckian curvatures there and high energies, etc. So
that's the place where this final state proposal is happening, right?
this final state proposal is, it's, yes, that whole diamond, which includes that part, is where the final state proposal is happening.
No, the fact that that area is 0 means that, am I not to be associate that to the fact that dimension of the projector is 1?
Yes, I'm just saying that in the final state proposal, they weren't so focused on that corner as they weren't associating the Hilbert space with that area. They were just saying the whole interior is projected onto a definite state. That interior does include that corner, so you can say it's related to that corner. They were relating it to the whole singularity because it's there in the whole diamond, but yeah, you can relate it to that corner. But the point is, there's no nice slice you can draw on which you would try to describe the quantum state where the area is 0.
Sure.
But maybe we can talk about this in the next talk, which is the situation we find where this is an issue is when you have closed universes. When you have closed universes, the area is not really there, right? So if you have some sort of closed universe that's entangled with some radiation, then the thing that plays the role of the area is just the entanglement entropies, the amount of entanglement that this universe has with what's outside. And
You have a closed universe, but there is an outside too.
yeah, so imagine that you have a situation where there's AdS, which is just entangled with some closed universe, which has a transition.
You're allowed to talk about this.
That's what we're going to talk about next time. Yeah, that's what we're going to talk
It seems a little, you might say you have a closed universe, you have a closed universe. There is some meta observer.
Forget about meta observer. This is just like some geometry you can draw.
No, but can you get it entangled also?
Yeah, you can get it entangled.
But what
How do you mean? You talk about geometry and how do you now entangle?
We'll talk about that next time.
I see. So, I'm allowed to say that, there's this universe, but there's another one.
Yeah.
Presumably, I can never send a signal to the other because it
That's
was
right.
close.
So that's the situation. That's the reason why it's different from the black hole scenario. Because in the black hole scenario, you could imagine someone who partly stayed outside and then went in, etc. So there was a lot of freedom in that sense. So you lose that when you do this. But if you believe everything we said so far, nothing in these calculations goes wrong when you try to do the calculation for the closed universe, and you'll just see that the errors are large. That's what's going to be the.
This closed universe also has a finite lifetime.
It has a finite lifetime, but there still exist nice slices on it.
Okay.
But it will be a gigantic universe with no large curvatures on that slice. But it has a future.
It has order 1 lifetime.
It can be made pretty big, I think. I think it can be made pretty big. I don't think there's a bound on how much time there is.
It's a Lorentzian geometry crunching.
Yeah, I think it can be pretty big.
It can be pretty big, and I see.
Like we can tune it.
And this really is the statement of basically A going to 0 limits.
Basically, the A goes to 0 limit done in a smart way. Yeah, that's
That it actually just
It's
was literally
literally
that
just
does
that.
not have area. So
Yeah.
clearly there's
So this is the reason I was saying that you can say that it's e to the minus 1 over g, so who cares? But it's controlled by A and or entropy or entanglement, and that really can
So then the issue that I was asking could be that we could be in a closed universe.
Correct.
How do we know
Correct.
that our
Exactly.
products are
Exactly.
But does it not bother you that we are there's no
Little-
possible experiment that can be done which allows you
Right.
you want to join this.
No. So going back to the
Einstein has turned in his grave.
going back to the spirit of complementarity.
Yes.
Remember that when we talked about complementarity in the last lecture, we very much focused on the description of a single observer. Now, in this new description of complementarity, we've gone back to talking about quantum field theory on curved spacetime. We've gone back to talking about just standard quantum field theory on curved spacetime, souped up with these new rules. These new rules, which is this non-isometric map from EFT to fundamental. That's it. We're now not talking about observers at all. And there's nothing wrong with this picture in terms of a QFT on curved spacetime solution.
That jump itself is so well justified,
Which jump?
Maybe the same point of view is an observer point of view. There's
So very good. We'll get to that as well. That could be. But I'm just saying this has this issue.
okay,
This
logical
So,
extension.
just to understand where you're going to go, you're going to say that there will be a big, arbitrarily big space,
Yeah.
which is encoded by a small finite number of degrees.
Correct.
So it's going to have to be very far from effective.
Correct. If you believe that the right inner product is the fundamental energy. Yes.
Some very radical.
Yeah, sorry, the basic question of one statement you said that A equal to 0, there is no AFT.
Yeah.
Yeah, but still you are saying that all these states will map to the single project single.
Sorry, can you say the question again?
So the one statement you said that at A equal to 0, there will be no EFT.
Right.
And the second statement you are saying that at A equal to 0, all this state in this bucket will map to the single projected state.
Right, but that's so there's two things we can say. When it's in the scenario where we had the black hole, when you have A equals 0, you don't have EFT anyway because there's a singularity within your Cauchy slice. Right? Does that make sense? Like because you have that corner.
No EFT in this sack. Right?
No, you have no EFT in this sack, yeah. And that is already a violation of EFT. Separately, there's the issue of this mapping to the fundamental Hilbert space being one dimensional. So whenever you have that, if you think the correct inner product for this observer is the fundamental inner product, then there's no chance of EFT, right? There's large corrections to EFT just from that fact. But because this thing had a slice which was anyway singular, maybe you didn't want EFT at all. Right? Like because why did you expect EFT when there was large curvatures on that slice? So now we're going to try to construct situations where we don't have that issue, and still we can have this separate issue, which is the fact that you're mapping a really big Hilbert space to a really tiny Hilbert space, and then you should see large corrections if you take that inner product space.
How big are these corrections in the closed universe?
It's controlled by the amount of entanglement between the closed universe and the AdS.
Which you could tune.
Which you can tune.
So I think this
It can be zero. Like 0 and 7.
I mean, it seems that these issues, with the Hilbert space being small and so on, they are associated with the existence of singularity.
Yes,
In your
in
future.
somewhere in your future or past, yeah.
In your future and past.
Yeah.
Then, even as a classical problem on such spaces,
Yeah.
Lorentzian,
Yeah.
can we really quantize space and get
Yeah.
get classical meaning, even just
I mean,
classically?
FRW has a singularity in the past. We do this all. We compute everything in cosmology.
Yeah, sorry, go ahead.
So I would say the thing you might wonder, so if there's finite time, you'll have finite energy resolution.
Yeah.
So if you could somehow link the time over which you
Yeah,
evolve
that would be nice.
to the number of states, to the dimensionality of space, that would be extremely satisfying.
But the issue is the thing that these errors are not controlled by the dimensionality of the space. It's controlled by the amount of entanglement with the asymptotic boundary.
Right.
And
So
that
it
can be
doesn't
made like really small, even if you have some very complicated.
So it doesn't sound like it's working.
I think not. At
But
least I
if there
haven't
was
seen it work.
something that made it work, it would be very satisfying.
Yes, it would be very nice.
Deciduous space, we don't quite know, right? I don't understand what this FR, you're talking about, but this, key issue, whether you do have a singularity in the past, that means you are in the single state. I don't see, it's not so obvious to me that, just semi-classical quantization will give you, a large number of states.
I mean, in cosmology, what we do is we consider states, say, at time right now.
Yeah.
It's perfectly reasonable classical data, just do semi-classical quantization of that. When you evolve that, eventually.
Gauss law, right? There's gravitational Gauss law.
The Gauss law. Yeah.
But in deciduous space, for example.
And deciduous space is very special because it's symmetric. So you have to be careful about this Gauss law because of what's called the linearization instability. You have to be careful in this. Rath has this paper about this other inner product, etc. But whenever you have a non-symmetric spacetime, there's no issue with it. You can just do regular QFT on curved spacetime. The Gauss law doesn't say much.
That constraint doesn't reduce it to you can have an infinite.
Oh yeah. Even with that, you end up with an infinite number of states.
Okay, just to ask you this. See, I was thinking the reason why you might want a single Hilbert space is that the entire notion of what is inside and outside is semi-classical. And one of the lessons you've taught us is that you can have topology changing amplitudes.
Yeah.
So there's not once you allow geometry to fluctuate, there's not even a clear notion of what is inside or outside, because you have all kinds of non-trivial.
Yes.
So just to ask you, in your case, will you have, non-trivial topological processes which allow the inside observer in some exponentially suppressed way to tunnel out to the
not as a saddle. What the observer can do is go from, so if I take two copies of this, then the observer can go from this closed universe to that closed universe. That's the observer can do. But they can't go from the inside to the outside in the sense of they can't get out to the asymptotic boundary.
To the asymptotic boundary.
Yeah, they can't get out to the asymptotic. At least there's no like on-shell contribution like that.
The fact that the closed universe is a density matrix which can be purified.
Yeah.
I mean, if you can't ever send a signal to whatever is purifying it, and no signal can be received, it should be utterly irrelevant, right?
Well, but I think you're basically saying the inner product should be the EFT inner product.
Yeah.
The fundamental thing should be irrelevant.
I mean, it seems, I
Yeah,
mean,
that's a valid perspective.
but you're going to show us, if you take the other view, here's all this strange thing.
Yeah, let's stop there.